Hey, hello, it's Unit 1, Section 4. Here we go. Let's look at these electrons. What are they doing? Alright, well, first of all, you know when you took that metal ionic compound and you put it in the fire? Well, what you're really doing is taking the outer electrons off of the metal. And when you heat it up, those electrons actually go up in energy. And on their way back down, they give off energy in the form of light. So this might be blue or red or yellow depending on how much energy is lost on their way back down to their ground states. Now, when you look at the periodic table, it's so cool because if you look at their Bohr models, you can see that they all have a pattern going either down a group or across a row. Definition of valence electrons would be those that are in the outer ring. So for example, in group 1, all elements have an outer valence electron of 1. Group 2 has 2 valence electrons. Group 3 has 3 valence electrons, and so on. Also, there's something called core electrons. Those are the other electrons. So for example, there are no core electrons in period 1 going across. In period 2 going across, everybody has 2 core electrons. Period 3, everybody has 10 core electrons. You get the idea. Noble gases. Well, it's kind of like this. Everybody wants to have their outer shell filled, just like a noble gas. Noble gases are already stable. That's why they don't react. All the other elements will react until they have a filled outer shell. So for example, if we look at sodium and fluorine, they've already transferred electrons to become more stable. So after sodium has transferred an electron to fluorine, they are Na positive and F minus. Now, because they have oppositely charged particles, they're attracted to each other and form a very strong bond. Now, you can see this one, calcium, it's got 2 outer electrons. What's going to happen? They're going to actually transfer over to oxygen. So this way, calcium will have an outer shell that's filled, and oxygen will now have an outer shell that's filled. What is the charge? Well, calcium will have 20 protons and 18 electrons. So that'll give you a 2+ charge. Oxygen will become the oxide ion with 8 positives and now 10 electrons since it gained 2 electrons. So it will have a 2- charge. Right, after a metal meets a nonmetal and electrons are transferred, you will have these charges. Know these. Remember these. These are the main patterns. Ionic compounds. The ions that you saw on the previous slide are used to help you figure out how to balance the charges to form the correct formulas. Now, I need to make sure I put an 8 here. Okay. For example, sodium, right here, has 1 outer electron. Chlorine originally had 7 electrons. So 1 valence transferred to the 7 valence add up to a total of 8. That makes sense. Notice their ions always, their charge always adds up to 0. Okay. Now, what if you get into more complicated ones? For example, magnesium, it has 2 electrons in the outer shell to give up, but chlorine can only pick up 1. So another chlorine atom is going to have to come in and pick up the other electron from magnesium. What do you end up with? MgCl2. So that's 1 magnesium ion, 2 chloride. The way we write it is name of the metal and then the name of the nonmetal with an IDE ending. A little bit more complicated here. As you can tell, magnesium hydroxide has an OH group as the name of an ion that's got 2 atoms. 1:2 ratio, just like magnesium chloride. Sometimes your positive ion is a molecule instead of, say, an element like sodium. Again, even though it has 5 atoms, just treat it as an entire unit just like you would sodium. So it's 2 positive ions will cancel a 2 minus. It's a 2:1 ratio, so we write NH4 2, and then we write the carbonate. What if the compound contains transition metals? How do we name them? Just remember, your ion charges have to add up to 0. Oxide is always -2. So this tells us we have a 2:3 ratio of these 2 ions. If you draw them out, you can see that each of these ions has to be a +3, or Roman numeral 3. So for transition metals, any of these in this D block, your charge is your Roman numeral. Just make sure you have the charge as the Roman numeral to specify which ion you're talking about. Writing electron configurations, pretty easy. Just remember your original Bohr model actually breaks down into an even more elaborate set of subshells. So we know this as energy level 1. That's the 1s subshell. Energy level 2 actually breaks down into the 2s and the 2p subshell. And 3s, the third energy level, is actually broken down into the lower energy s, then the intermediate p, and then the higher 3d. So this is another way of looking at it and of reading it. So if, for example, we did sodium, its electron configuration would be 1s2, so that's reading the first 2 electrons in the first ring. Then we would go to the second ring and read these 2 electrons, so it would be 2s2, and then travel across here. So you're reading this table like a book. Second row, this is called the p subshell. Read all 6 electrons, so it would be 2p6, and then finally going to row 3, 3s subshell s with 1 electron. This is where sodium would be, atomic number 11, or the 11th electron. So this would be 3s1. So the way to write the electron configuration is to first identify the atomic number and make sure all those electrons that you mapped add up to 11. So 2, 2, 6, and 1. This is basically a mapping of your electrons. That's it. We'll see you next time. Goodbye.